Hello everyone. So in the previous lecture, we discussed the assumptions and theory of the working stress method. In today's lecture, we will focus on the analysis of RCC sections using this method. So what is analysis? So analysis means, in case of RCC, finding the moment of resistance or finding the safe load a given section can carry without causing any failure, or estimating the stresses developed in concrete as well as in steel. So we will understand this concept through three numerical problems that we are going to discuss in this lecture, each highlighting a different behavior of RCC sections. Let us begin with the numerical example 1. Here, an RC beam 300 mm by 700 mm is reinforced with 320 mm diameter bars. The centers of the bars are 50 mm from the underside of the beam. The maximum stresses are not to exceed 7 Newton per mm square for concrete and 190 Newton per mm square for steel, with a modular ratio given as 13.33. So determine the moment of resistance and safely distributed load the beam can carry. The span of the beam is 6 meter. So in this problem, we are required to determine, one is the moment of resistance and the two is the safely distributed load the beam can carry. First, we can calculate the effective depth of the beam by subtracting the effective cover from the overall depth. So they given the overall depth is 700 mm. Okay, the overall depth has been given as 700 mm, and they are given the cover as 50 mm. The effective cover as 50 mm. So subtracting this 50 from 700, we will be getting the effective depth of the beam as 650 mm. Next, we can calculate the area of the steel. So area of 120 mm diabar is pi by 4 into 20 square. Whereas this beam has been provided with 320 mm diameter bars. So total steel area will be AST is 3 into pi by 4 into 20 square, which comes around 942.48 mm square. So using the transferred section method, we can locate the neutral axis and we can compare it with the critical neutral axis depth. So the depth of critical neutral axis can be calculated by using the relation that we have already used in the previous slide. XC will be equal to 1 divided by 1 plus sigma ST by M into sigma CBC into D, where sigma ST is the permissible tensile stress in steel, which has been given as 190 Newton per mm square, and M is the modular ratio, which has been given as 13.33, as well as sigma CBC is the maximum compressive stress in concrete under bending, which has been given as 7 Newton per mm square. And D is the effective depth of the beam. Just now we computed that value can be taken as 650 mm. So substituting all the values, we'll be getting the depth of critical neutral axis as 260 mm. Next, this has to be compared with the actual depth of neutral axis. So the actual depth of neutral axis here in this case, the area of the steel has been given rather than other things. The area of the steel has been given. So directly we can use this formula, bx square by 2 will be equal to m into ast into d minus ex. So since we are going to find the actual depth of neutral axis, so here we are providing x as xa. That is the notation for actual depth of neutral axis. So since all the values are known except the value of xa, that is b is the width of the section, which has been given as 300 mm, and then m is the modular ratio 13.33. AST is being calculated as 942.48. D has been taken as 650, which has been already calculated. So using this one, we'll have a relationship in terms of XA. So once XA, this equation has been solved, we'll be getting the value of XA, which comes around 195 mm, which is less than 260 mm. That is the critical depth of neutral axis. So from this comparison, we observed that the steel reaches its permissible stress before concrete. Hence, the section is classified as under reinforced section. So for under reinforced section, the moment of resistance is governed by steel. Hence, moment of resistance MR will be calculated as T into Z, where T is the total the total tensile stress, whereas Z is the lever arm. So using the relationship, T is sigma st into AST, where Z is D minus XA by 3, where all the values are known. Sigma st is being given as 190, AST we calculated, D is 650 mm, XA has been calculated now. Substituting all the values, we will be getting the moment of resistance, which comes around 104.76 kilonewton meter. Now, in order to get the required values, this will be equated with the ultimate bending moment or the maximum bending moment. So the maximum bending moment, assuming the beam is a simply supported beam, will be getting the maximum maximum bending moment formula as WL square by 8. Whereas W is the total load which will be acting on the beam, which includes its own self weight in addition to the externally applied loads. So substituting the values of the span, which has been given as 6 meter, we will be getting the maximum bending moment as 4.5 into W. So equating these two, that is maximum bending moment and the moment of resistance, we will be calculating the total W. This W represents the total load which is acting on the beam. It's been calculated as 23.28 kilonewton per meter. But the question is, we need to find the safe load the beam can carry. That is nothing like the live load which will be acting on the beam we are supposed to calculate. So how to calculate the live load is, since the total load is known, so in this one we will be deducting the self weight of the beam so that the live load can be computed. So for which the self weight of the beam will be calculated. So self weight of the beam is the cross section, the overall cross section, B into overall depth into the unit weight of the concrete, which will be taken as 25 kilonewton per meter cube. So all the values been written as meter. So 0.3 into 0.65 into 25 will be getting the value of the self weight, or otherwise in this case the dead load, as 5.25 kilonewton per meter. Now the question is, live load only we need to calculate. Therefore, the live load carried by the beam WL will be equal to the total load minus the dead load. That is 23.28 minus 5.25, we will be getting the total live load which will be acting on the beam. That has been computed as 18.03 kilonewton per meter. And this is what has been asked. Now let us move on to the numerical example 2. So here the question is, determine the safe load carried by a slab 120 mm thick effective if it is reinforced with 12 mm diameter bars placed at 80 mm centers. The slab is simply supported over a span of 3.2 meter. Take sigma CBC as 7 Newton per mm square, sigma ST as 140 Newton per mm square, and modular ratio as 13.33. So as similar to the previous problem, first thing is that we need to find the area of the steel. So previous problem, it was a beam wherein the diameter of the bar as well as the number of bars were given. So easily we computed the area of the steel provided. Now coming on to the slabs, there will not be any provision of number of bars will be given. Instead, the bars and spacing which will be provided over a 1 meter span alone will be given. That is what has been given: 12 mm diameter bars spaced at 80 mm centers. So using this only, we are supposed to calculate the area of the steel. So the area of the steel provided will be calculated using the relationship area of 1 bar divided by the spacing into 1000. Since we are taking it for 1 meter, that is why this 1000 has been given. So area of the 1 bar is pi by 4 into 12 square divided by spacing has been given as 80 mm. Using these values, we can calculate the area of the steel as 1413.72 millimeter square. Again, using the transformed section method, we need to locate the neutral axis. So depth of critical neutral axis will be computed with the same relationship 1 by 1 plus sigma st by m into sigma cbc into t, in which sigma st has been given as 140 Newton per mm square, sigma cbc has been given as 7 Newton per mm square, and m has been given as 13.33. In this case, the effective depth, that is the thickness, effective thickness has been given as 120 mm. That is nothing like the d value. So substituting all the values, the depth of critical neutral axis has been calculated as 48 mm. Now for calculating the depth of actual neutral axis, we'll use the same relationship. Bx square by 2 will be equal to m into ast into d minus x. Again, instead of putting the value as x, we'll be using the term as xa in order to differentiate from the critical to the actual depth of neutral axis. So here B is known, the depth of the section, since we are taking it for 1 meter length only, so B will be taken as 1000 mm. XA only we need to calculate. M has been given 13.33. AST has been calculated 1413.72. D is known, which has been given as 120, and XA is an unknown. So substituting all this value, you'll be getting a relationship in terms of XA. So solving this equation, you'll be getting the value of actual depth of neutral axis, which has been computed as 51 mm. Which is greater than 48 mm that is being calculated for depth of critical neutral axis. So from this comparison, it has been observed that the actual neutral axis depth with the critical neutral axis, we found that the concrete reaches its permissible stress first. Hence, the slabs behaves as an over-reinforced section. So in over-reinforced sections, the moment of resistance is governed by concrete. Unlike the steel, what we are considering in the previous case, in over-reinforced section, the moment of resistance is governed by concrete. So using the permissible stresses in concrete, that is moment of resistance, MR will be equal to C into Z, where C is the total compressive force and Z is the lever arm. So B into X into sigma CBC by 2 into D minus X by 3. Substituting all the values, we will be getting the moment of resistance, which has been calculated as 18.39 kilonewton meter. And the maximum bending moment, again assuming the slab is a simply supported one subjected to a UDL. So M will be calculated as W L square by 8. Where W is the total load which is acting over the slab, including its own weight. Right. Since the span has been given as 3.2 meter, so this maximum bending moment will be calculated as 1.28 W. So equating the maximum bending moment with the moment of resistance, we'll be calculating the total load the slab can withstand without any failure. And this value has been calculated as 14.37 kilonewton per meter. Again, the self height has to be calculated. So the self height of the slab will be B into D into unit weight of the concrete. And in this case, B is nothing like a 1 meter length only we are considering. That's why B has been taken as 1. And capital D is nothing like the overall thickness of the slab. Right. So the small d only has been given as a 120 mm. So assuming the diameter, we can find the overall depth assuming some clear cover or effective cover. The overall depth of the section has been taken as 0.146, that is 146 mm. And the unit weight of the concrete has been taken as 25. Multiplying these values, we will be getting the self height of the beam as 3.65 kilonewton per meter. Now our question is, we need to find the live load which is carried by the slab. So WL will be equal to W minus WD, which will be 14.37 minus 3.65, will get the value as 10.72 kilonewton per meter, which is what asked in the question. Now moving on to the numerical example 3. In this case, a beam 350 mm by 650 mm is reinforced with 4 numbers of 20 mm diameter bars at an effective cover of 35 mm. If the span of the beam is 7 meter, estimate the stresses developed in steel and concrete if the beam carries an UDL of 20 kilonewton per meter, which inclusive of self weight, and take M is equal to 13.33. So in this case, we are required to estimate the stresses developed in concrete and steel. As we know, using the transformed section method, we need to locate the neutral axis position, and once the neutral axis is known, we will apply the bending stress equation to determine the stresses in steel as well as in concrete. So now area of the steel will be calculated. Since it is a beam, area of 1 bar is pi by 4 into 20 square. Since 4 bars has been given, 4 into pi by 4 into 20 square, we will be getting the area of the steel provided is 1256.64 mm square. Now depth of the actual neutral axis is bx square by 2, which will be equal to m into ast into d minus xa. And this problem, we are supposed to find the stresses. That's why directly we are finding out the depth of the actual neutral axis rather than finding out the critical depth of neutral axis. So substituting the values, the width of the beam has been given as 350, modular ratio has been given as 13.33, area of the steel is being calculated as 1256.64, and the effective depth, which will be calculated deducting the effective cover from the overall depth of 650 mm, we will be getting it as 615. So solving this equation, we will be getting the actual depth of neutral axis, which is calculated as 199.44 mm. So the lever arm will be calculated as d minus xa by 3. So since all the values are known, we can calculate the lever arm value, which will be calculated as 548.52. So now we need to calculate the stresses in steel as well as in concrete. For finding out the stresses in both the materials, we will be using two different cases. One is equating the bending moment, that is the maximum bending moment, with the moment of resistance, considering it as an under reinforced section. And another case is equating the same maximum bending moment with the moment of resistance, assuming the section is an over reinforced section. So equating this maximum bending moment with both the moment of resistance, we will be computing the stresses in steel as well as in concrete. Now let us start with the first case, in which the maximum bending moment will be equated with the moment of resistance, considering it is an under reinforced section. That's why AST into sigma ST has been taken. So the maximum bending moment, considering a simply supported case, the formula will be WL square by 8, in which the overall load has been given, that includes its self weight as 20 kilonewton per meter, and the span, effective span, has been given as 7 meter. It will be calculating the maximum bending moment as 122.5 kilonewton meter. And this will be equated with the moment of resistance, which will be calculated using the formula AST into sigma ST into Z. So AST, which has been calculated as 1256.64, sigma ST only we need to find it out, and Z has been calculated, there is a lever arm 548.52. So equating these two, we will be getting the permissible stress in steel as 177.72 megapascal. Similarly, the maximum bending moment of 122.5 kilonewton meter will be equated with the moment of resistance, considering it as an over reinforced section, in which the moment of resistance will be computed with the formula Bx into sigma CBC by 2 into Z. So since all the values except sigma CBC is known, we can substitute all the values in that equation and calculate the value of sigma CBC, which has been calculated as 6.4 megapascal. So this calculated stresses in concrete and steel are then compared with the permissible values. In these cases, you can see sigma ST is less than 190 megapascal, the maximum permissible, and sigma CBC, which is less than 7 megapascal, that is the maximum permissible stresses for both the steel and concrete. If the stresses are within the permissible limits, the section is considered safe under the given loading condition. So this example demonstrates how the working stress method is used to check the safety of existing RCC sections. So to summarize this lecture, working stress method is used to analyze RCC sections. The sections may be either under reinforced or over reinforced. The moment of resistance depends on the governing material, and the stress analysis ensures safety under service loads. In the next lecture, we will proceed to the design of RCC sections using the working stress method. Thank you.